So last week we talked a lot about velocity. We talked a lot about velocity time graphs, position time graphs. We want to go one step further today, and we're going to talk about the last of our kinematic variables, acceleration. And then we're going to show how that kind of fits into the whole big picture as well as we go through. So I want to start off with this. If an object is accelerating, by definition, what do we mean? It means that its velocity is changing. So we define velocity as something position changing. We're going to define acceleration as something velocity changing. I just totally blanked out on what I meant on this first one here. Give me a second to pull up my notes. Why did I make it that way? Yeah, okay, that's just what I was saying. All right. Acceleration is to velocity. Acceleration is a change of velocity. Just like velocity is a change in direction or position. At any point you take calculus, calculus is where these are very much related. And it comes out very naturally with that math. Doing with algebra, it's a little bit not so clear what the connections are, but we just talk to them. So we talk about velocity being the rate of change of position. The average is delta x over delta t. What do you think? We're going to say that acceleration is the velocity, like velocity is position. How would we write the next equation then? How would we write our equation for acceleration? Let's do our average acceleration equal to delta v over delta t. We're going to place our position with velocity. We're going to place our velocity with acceleration. We look at those equations, they fundamentally look the same. They're different things we're talking about, but their mathematical shape, if you will, is the same. Here's one I want you to think about a little bit. Does acceleration have a direction? Acceleration have a direction? What do you think? How many vote for no? Couple? How many vote for yes? Well. We talked about velocity having a direction. Yes, acceleration has a direction as well. Which direction is your velocity changing? Is your direction increasing to the right? Is it decreasing to the left? Talk about a couple different ways. To kind of make this a little bit more clear, I'm going to go through 4 examples here. Say we're out here on County Line Road, and we're heading east. We're heading towards the reservoir. And our car is speeding up. What direction is our acceleration? Which direction is our acceleration changing? It's changing to the east. We're going faster to the east. Velocity was, let's say, 35 miles an hour, and it changed to 40 miles an hour. Increased it, so it's going faster to the right. Now, if our car is heading east and it's slowing down, which direction of our change of velocity this time? Now our velocity change is going the other way. So we'll do west. So we'll do west. So I can kind of draw this. Say we're moving to the east. I can draw an arrow like that. And let's say we're accelerating. So a moment later, I can take that same arrow. I'm going to draw it like that. What's the change between these two arrows? We added this little one in here. That's why I went from the top arrow to the bottom arrow. What direction that little arrow faces? It faces to the right. It's east. Now we can flip it around. What if we're still traveling to the east like we are on that second one? Let's keep going to the east. We're slowing down by drawing an arrow again, right? The size of the arrow gives you a relative idea. Is it bigger or smaller? Is the number different? So I have a shorter arrow here. We're slowing down. What's our change? How do we go from the big arrow to the little arrow? We had to have a little arrow pointing backwards, west. Be our acceleration. So I can write this in math. Right, this is our initial velocity. This is our final velocity. Our acceleration. There's a relationship between these, just like there was with position. I could say I started at my desk, and I walked over to one end, but then I turned around and walked back. I'm not as far away as I was when I started. That's the same kind of thing we're seeing here with your acceleration. I don't want you getting confused with slowing down, meaning a negative acceleration. Slowing down doesn't necessarily mean it's a negative acceleration. Negative tells you a direction. Positive tells you a direction. Slowing down doesn't tell you a direction. Yeah.
Would it just be like backwards acceleration? Or
That's one possible way to think about it. But I want you to be careful. Backwards again implies a direction. So it's good. I'm glad you're making the connection that acceleration has a direction. I just want to be careful with how we understand what that direction is. Anytime your velocity changes, speed up or slow down, and actually we're going to see a little bit later, the direction of your velocity changes. The Earth's circling the sun. The Earth is accelerating as we circle around the sun. Our velocity is changing direction. Changing magnitude, we're not speeding up or slowing down. We are a little bit. We're not a perfect circle. I want to get you used to this idea. I'm going to be drawing little arrows like this. The arrow represents a vector. The arrow has a direction. We define to the left as always being negative. In this case, we define left being west. So what would this bottom one be? This next one be? If we drew that one, we're heading to the west, speeding up. And so our final velocity is going to be bigger. What do we need to do? What do we have to add, if you will, to our top arrow to get to our bottom arrow? You have to add another arrow like that. Acceleration is to the west, or acceleration is to a negative direction. And west tells you a direction, just like negative tells you a direction. It's just a different terminology. Up, down, left, right, east, west, north, south. They all are directions. How about this last one? If the car is driving to the west, but it's slowing down, which direction is its acceleration? Car is driving to the west. But slowing down. What arrow do we add to our top one to get to our bottom, so that our sum is the bottom one? You have to add a little arrow going to the back to the right. Acceleration here is to the east or positive. What did you have? How did you have to change your velocity? That's going to be your definition of your acceleration. So what I want you to see, here we have speeding up. We can have it going to the east. Here we have speeding up. We can have our acceleration going to the west. Speeding up has an associated direction to it. You're speeding up in what direction? Speeding up in a positive direction, or you're speeding up in a negative direction? That makes a little more sense once we get into a few more examples. You guys seen stuff like this where you talk about putting arrows together, or is that really something new? Done anything like that in your math class? Take arrows and them together? Okay. I'll spend some time tomorrow and I'll figure out a way to explain that a little bit better using the arrows. Because the arrows are a good visual and makes it really simple to understand. The key thing I want you to get out of this is acceleration has direction. That's whatever direction our velocity is changing. Not the direction we're headed. What direction is our velocity changing? The SI unit for acceleration. What do we use? What units do we use to measure velocity? Can you tell me that? What do we use to measure velocity? Meters per second. So if our velocity is meters per second, we're dividing this by time, sort of the second down here on the bottom. Usually we'll write this as meters second squared. When you took physical science class, you probably hopefully you talked a little bit about gravity. Not sure what units they would use in a physical science class. Gravity is an acceleration 32 feet per second squared, 9.8 meters per second squared. The reason I'm going there is I'm trying to tie back to something you perhaps would have seen in the past, where we use the units meters per second squared. You'll hear me oftentimes really focusing on units because they're important. They're going to help you do two things. They're going to help you get your head meters per second squared. That's an acceleration. I want you to be able to make that connection. The second thing that they're very important for is whenever we're doing calculations, not only are you doing calculations with your numbers, you're doing calculations with your units. You can always keep your units straight. If you keep your units in place, it'll help you make sure that you've done your calculation right. If you set your calculation up wrong, you're not going to get the right units at the end. That should go ding, ding, ding. I've done something wrong. When you look at two numbers and you multiply, you can't tell us how to look at your numbers if you do something right or wrong. It doesn't tell you anything. This is just a number. Units are what's going to be meaningful. All right, let's do some examples. So I want you to do these very similar to what we did before. Right, we have our equation. Equation A equals delta V over T. So I want to do the same kind of thing here. I want to have delta V, delta T, and our A. I want you to write those three variables down. After we're going to look at our word problem, we're going to identify things so we can write them out. The sprinter starts the last 100 meters of a 400-meter race. She increases her velocity from 7 meters per second to 9 meters per second over a period of 2 seconds. So what are we seeing in here? Well, there's some things in here that are extraneous. They don't tell us anything. We could do a couple things. So this last 100 meters, we could call that a delta x if we wanted. Really what that is, measuring the distance between 2 points. We have a velocity from 7 meters per second to 9 meters per second. So this, hopefully you're catching, is a VI. 9 is a VF. And we're giving a period of 2 seconds. There's a delta T. It's asking us to find her average acceleration. So I'm going to put a question mark right away next to the acceleration. What is it? Find, where, whatever you see those, that's our question mark. So we need to figure out from our problem, what are these other two? Well, it's easy to figure out delta T, right? They told us it's 2 seconds. How about delta V? Delta V is the change in our velocity. But we also can write it like this, VF minus VI. That's how we figure out the change in our velocity. Put in our numbers, 9 meters per second minus 7 meters per second. 2 meters per second. Yeah, I want you to keep your units on these. Don't just write a number without a unit. So now we're ready to plug it in. We've got everything identified. Let's plug them in. Two over two, they're going to give us 1 meters per second over seconds. What I'm hoping you see here, this is the same functional form that we saw for velocity. A equals B over C. Whatever you want to call A, whatever you want to call B, whatever you want to call C. So the math we're doing here is going to be the same thing we did with the math we saw with our velocities. Same thing, just a different symbol. It might take a little while doing a couple of these for that to get more comfortable with that concept. Math class, right? Your teacher sometimes use A, B, and C. Sometimes they should use X, Y, and Z. Sometimes use other things. It's just a symbol. What's important is how those symbols are related to each other. And in this case, we have a relation. A equals delta V over delta T. Do another one. Again, first thing I want you to do, I want you to write down the variables in our acceleration equation. Now let's look at our problem and see what we can identify. Drive south. Well, there's something key. Driving south on a freeway. It speeds up from, so it's starting at from 45 miles an hour. There's your initial. To 65, there's your V final. Over a period of 5 seconds, so there's your delta T. We want to be careful here. What direction is the car traveling? South. 45 miles an hour south. Well, south isn't something you put into a math equation, right? What's south mean? A math equation. We're going to find south as being the negative direction. So what's our velocity really here? It's negative 45 miles an hour. It's negative 65 miles an hour because it's going south. It's going in the negative direction. We can do math with negative signs. What is it with south? So let's go ahead and figure out what we want to do. Again, it's asking us what is our acceleration. So I want to put a question mark here next to our acceleration. We got a 5 for our delta T. 5 seconds. What's our delta V? Well, it doesn't tell us how much the speed changed. It tells us what we started at, what we ended at. So we've got to calculate what that speed change is. Again, how do we calculate it? VF minus VI. That's negative 65 meters per second. Minus negative 45. I always taught how to do math. You guys taught the same thing as you subtract the negative. I can make it positives. Okay. Otherwise, I get myself horribly lost. Yes.
It says miles per hour for the two speeds.
Oh, sorry. Good. This should be MPH. So what's our change in velocity here? 20 mph. I do want you to see something here. This problem is not very friendly to us. We could do things in a couple different ways. Well, let me do it this way, and then I'll show it to you at the end. It'll make more sense. It'll make more sense. So we want to figure out what our acceleration is. We've got our delta V, we've got our delta T. Plug things in. Delta V, negative 20 miles per hour. Delta T, 5 seconds. What's our answer going to be here? We're going to do 4 miles per hour per second. I just kept my units here as I went through.
Is it, miles per hour?
This is where it gets confusing as well. I think I'm very clear. So what was our velocity here? 2 miles per hour.
Yeah.
We have miles per hour on the top, we have seconds in the bottom. Calculation as it stands, we're talking about miles per hour per second. As opposed to the first one here, our velocity is in meters per second.
Yeah.
So we have the 2 seconds there.
Stay.
Good, yeah, keep the units the same. Now this is a really weird unit. 4 miles per hour per second. But we're so used to talking about velocities of cars being in miles per hour that if we change this, how could we change this? We could change this to be the seconds, we can convert that to hours. How do you convert seconds to hours? Seconds are in an hour, our seconds are cancel each other. If we did this, then we could have whatever that number is. That's really been huge, what, 120, 144.
Yeah, it'd be negative like 14,400.
Per hour squared. But so we have the same timing here, so it's not miles per hour per second. We could have done it easily the other way. We could have converted the top of the miles per hour. We could have converted that into miles per second. The point I'm trying to get to is, does this mean anything to you? Is that big or small? Well, it seems it's a big number. But we're all used to this. We know 4 miles an hour. We know what that feels like. So if we're accelerating at 4 miles per hour per second, that means it's going to take us 10 seconds to get up to 40 miles an hour from a standing stop. I consider that probably a pretty slow acceleration for a car. It takes 10 seconds to go from 0 to 40. By your sports cars, you go and get a high-end sports car, it's like 0 to 40 in 3-something seconds. Yeah, right about 3.5.
Especially if you mod it.
Especially if you mod it. I have a Corvette. Oftentimes going find a place to enjoy, okay, how fast is the sucker accelerate? Pretty damn fast.
Even though you know how fast it is, better mind yourself.
Dangerous as all get out. You have to do it in a very safe place. You don't do that like on a closed track. Otherwise, you're asking for trouble.
Once you do fast cars, you can also watch the Fast and Furious movies.
Yep, you got some nice cars there too.
Always drives a fast car.
So the whole point I'm trying to make here with these units is sometimes it looks weird, but we're used to seeing things like this. We know what 4 miles an hour is. 4 miles an hour, we have an idea what that speed is. And if we talk about how fast we're changing that, and we talk about how fast 4 miles per hour per second, we can look at that and say it's probably a pretty slow acceleration for a car. We look at it this way, we're not used to looking at things like that. It's not as meaningful to us. So sometimes we have to be careful what units we pick. They're both correct. These are the same thing, just said different ways. Just sometimes one's a little bit more meaningful. So how many of you know more than one language?
I'm trying to learn.
A couple of you know more than one language. You could say something in one language, something in another language. I know German. If you say something to me in French, I have no freaking clue what you're talking about.
I actually take French.
So to me, this is like French. I have no idea what that means. I understand what the number is, but I don't know what it means.
French is a little bit confusing too sometimes.
And French is confusing, yeah. the whole point I'm making is it's the same thing. You could say fast car in French, you could say fast car in English. They both mean fast car. But you say fast car in French, I don't know what it doesn't. I need some more context. This is the better context in this case. Usually I won't do problems where you're getting mixed times like this. This is horrible. It tends to be the English system. We tend to use that MPH. We use that every day. Yeah. Converted to meters per second? Yeah, that's fine. That's perfectly fine. You could do it in any number, any symbol, any units you want. Meters per second, meters per second squared, meters per hour squared, meters per hour per second, whatever. One of them's going to be more meaningful, is all I'm trying to say. One of them's going to be more meaningful. So what's another one here? We're used to getting on a bathroom scale and it tells us how much our weight is in pounds. There's another unit in the English system called a stone. The mass. Somebody walks up to you and says, hey, I weigh 7 stone. Doesn't mean anything to it. We don't know what a stone is. We're not used to that. That's kind of what I'm saying here. We're not used to miles per hour squared. That unit is not something we're comfortable with. You see miles per hour per second. That's units more meaningful to us. All right, kind of got off to the side there. I apologize, but what I want to get through is how you set it up. Take your the variables, put them in the left, do your calculation. Let's do the next one here. We can also rearrange our equation like we did with our velocity equation. And we can get different equations if we want to find for delta V or delta VF. So how do we do that? We start off with A equals delta V over delta T. I'm going to move that over a little bit. If we want to get that V by itself, delta V by itself, what do we do? Here we're dividing by delta T, so we get the opposite. It's going to be to multiply by delta T. I do the same thing to both sides. This is why I went through all that math that one day. I've just spent some time just going over math. What's our operation division? We do the opposite. That's multiplication. We multiply one side, we got to multiply the other. What does that give us for an equation? A delta T equals delta V. All we do is just argue about that. We can take it one step further. What's delta V? VF minus VI. So I can take this now, this whole thing. Let's rewrite this a little bit different. Let's solve it for VF. How do we solve it for VF? Add a VI to both sides. And now what do we have? VF is equal to VI plus A delta T. All I've done here was just some simple math with our simple explanations of what that delta means. And depending on how the question's asked, this may be a form of the equation you might want to use. This might be a form of the equation you want to use. This might be a form of the equation you want to use. They're all the same equation, just written differently. Like, if I say it this way, in English, we call it the red car. In French, we call it the car red, I believe. I believe the French put their adjectives after the noun. Saying the same thing. If we just rearrange things. Is this math confusing? Should I spend some more time talking about math? I want to make sure we're comfortable with the math before I go back to talking to it. A couple heads nod. It's okay. Good. If you are uncomfortable with this, reach out to me. We'll see if we can find some other ways to talk to be able to get that be a little bit more comfortable. All right. So let's do this. just put a box around the three equations that we have here. Again, these are all the same thing, just written in a different way. Now we can use these to solve some of our problems. Let's go look at problem number 3 here. Runner has an acceleration of, Runner has an acceleration of 3 meters per second. So there's our acceleration. There's 5 seconds. It doesn't tell you it's a time, but we know by its units that this is a time. How much is his velocity change? The same velocity change, we're asking for delta V. So I want to just start out the same way we always do. Let's write down our variables. Our problem, A told us was 0.3 meters per second squared. Delta T told us was 5 seconds. Delta V told us that's what we want to know. So we should use the form of our equation that has delta V. Again, I put the units there. The units are your friend. Why do I say the units are friend? Because look at this. What do we have here? We have a second in the top. We have second squared to the bottom, so that second's going to cancel out the square. What are we left with? Our units are meters per second. Good, that's what we want. Velocity is measured in meters per second. Now, if I would have made a mistake writing my formula, instead of multiplying by 5 seconds and divided by 5 seconds, then my units over here wouldn't have come out to be meters per second. They would have come out to be meters per second cubed. Hopefully that goes ding, 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 ding. That's a really weird unit. We don't know what meters per second cubed is. Must have made a mistake someplace. So units are your friend. It will help you double check yourself. The next one here. Yeah, I want to start off with delta V, delta T, A. Car starts from a standstill, accelerates 15 miles an hour for 4 seconds. What's its final velocity? Here's our A. Here's our delta T. It's asking for final velocity. What else did the problem tell us?
Tells you the initial 0.
Tells you the initial is 0. Good. And if you're comfortable reading word problems, then go ahead. I don't care if you skip this step here, writing things in the margin. What I'll tell you is, it really will help keep you straight. And if you write something down in a problem and I say, okay, you correctly identified what your units were, what your variables were, where was the mistake? The mistake was you just wrote your formula. Then I can figure out where I can give you partial credit. I would recommend doing this if you're not at all comfortable. If you're comfortable, go ahead and skip past it, but make sure your answer's right. So let's look at our delta V. Let's start filling in things. We have 15 miles per hour per second. Kind of an odd unit, but it's one that it looks odd, but it's one that we're used to. We have a delta T of 4 seconds. That must mean we're trying to find we can find our delta V. So let's go ahead and do it. Delta V, A delta T, 15 miles per hour per second. That's 4 seconds. Again, our S's are going to cancel, so we're left with 60 miles per hour. Good, miles per hour, that's velocity. just further than asks us, it wants to know what our final velocity is. Well, we know our initial velocity is 0. We know our delta, our change in velocity is 60. So let's look at what's our formula for our change in velocity. Now, I could have also written this out as the long one that I have up above, but I want to do it in 2 steps, and then we'll show you one. We have delta V plus df minus di. Or we can write this as df equals delta V plus di. Delta V we know is 60. Di we know is 0. We know we have a df of 60 miles per hour. So here we could do that in 2 steps. I'm figuring you guys are more comfortable with that. Boy, that writing is horrible. Let me do that again. I did that in 2 steps, solve the 2 equations.
Teachers and students, pardon this interruption. Cohort A, thank you for a great first day back. At this time, we may now release all car riders and all walkers. Please exit a door that is not the front doors. At this time, you are released. If you're getting your items from the balcony straight room, if you're an after-school athlete, the auxiliary hallway bathrooms and the stadium bathrooms are open for you to change prior to your workout. And all bus riders, of course, the 125 bell, you may be released out their front doors.
Both.
Thank you very much, all. Have a great Monday, and we'll see you back here tomorrow.
So guys, yeah, so just to make clear, on every day, whether you're remote or whether you're here with me, if we do a Mondays and Tuesdays, the goal is a lecture point quiz. I want you guys to answer it whether you're here or whether you're remote.
Honestly, I actually forgot like the first week that there was like lectures on Mondays and Tuesdays. And I was just like, I like remembered right when it was over and like it was too late and I was like, shoot.
Just go back and look at them. The lecture quizzes are always open. Did you take the Friday quiz then, or did you not do that? If you haven't taken the Friday quiz, just let me know when you
I'm gonna check because I might not have. I don't know for sure, but I'm definitely gonna check.
Yeah, double check. The quiz from Friday? Yes. What time would you like it open?
Today, at like 6.
Open up at 6. Open up. Perfect. Write that down though, so I don't forget it. So I'm looking that up. So this is the V graph. 6 o'clock. Okay.
And this one, because I was like in class, but I didn't think we had to do it.
It should be open. You should be able to go right into it and just put down that you were in class that day.
Alright.
Awesome.
I wish I could use this velocity and like acceleration stuff in my game with like all my fast cars, but I can't because it never gives you numbers. It never does.
At some point, I'm going to try to get away from the numbers.
Because all the game does is show bars, and there's like 5 bars.
It's visual.
Yeah. And like, you can kind of tell because there's like pickup trucks, and like some of them have very low. It's like 1 and a tiny bit of the second bar. Those ones are super slow. And then if you look at the sports cars, they normally either have all 4 or they have all 4 and like half of the 5th one. That's how you have to tell in the game. It's somewhat annoying.
Somewhat
sometimes.
visual. Yeah. Cool. Have a good day, everybody. Hope this stuff wasn't too hard today after what a couple of days there.
No.
Yeah, if you have any questions or needs.
You said the Monday and Tuesday stuff, that's always open?
Yes. Mondays and Tuesday stuff's always open as a participation with quizzes.
Next couple of days, next week. It's
Sure, be happy to do that. Yeah, before you, if you're not sure what if you're not sure you're ready to take the quiz, let me know. We can spend a little bit of time talking about it and make sure you're up to speed. I'd rather you talk to me first and do well the first time.
Are you supposed to leave your computers here?
Yes, I'm sorry, yes, leave your computers here. Yes, because that's all your teachers have to return the computers. Cool.
See you tomorrow.
Take care, Connor.
Yeah, all right. Tomorrow morning, right?